All right, well, thank you for joining us for session 5 of the NADP-clad Critical Loads of Atmospheric Deposition seminar series. My name is Mike Bell. I'm an ecologist with the National Park Service Air Resources Division, studying how air pollution is impacting national parks. So we're trying to bring together a cadre of scientists and land managers who are working with the data showing the impacts of nitrogen and sulfur deposition on natural ecosystems. Today we have 3 great speakers in Jason Lynch, Todd McDonnell, and Leora Nanus, who are going to be speaking to critical loads of nitrogen and sulfur for aquatic systems. Okay, this is the 5th of a 7-part seminar series. The last 4 are available on the NADP website, a link of which was provided in the meeting invite and will be sent out with a recording of this information afterwards. I really hope you can join us for our final 2 after today, which will be June 30th and July 28th, to talk about critical loads of nitrogen for soils and mycorrhizae, and then looking at a general synthesis of all the information that we've seen over the last 7 months or 6 months. So this is part from comes from the National Atmospheric Deposition Program, which is based out of the Wisconsin State Lab of Hygiene in Madison, Wisconsin. NADP has been monitoring deposition of air pollutants for over 43 years and has 5 national networks measuring air pollution across the U.S. The largest of which is the National Trends Network, which measures wet deposition and has 263 active sites, which you can see kind of in this map here, showing the site locations as well as the comparison and concentrations of wet deposition of nitrogen. Within NADP, there are 4 science committees. There's CLAD, the Critical Loads of Atmospheric Deposition, TDEP, which is looking at total deposition, which integrates measurements and modeled values of deposition, AMSC, which is the aeroallergens, looking at how allergens are transported and concentrations across the U.S., and MELD, which is looking at mercury deposition and impacts in the atmosphere. We as CLAD facilitate the technical information sharing on critical load topics with a broad multi-agency and entity audience, with the intent of filling gaps in critical load developments in the U.S. Critical loads being that threshold below which impacts to ecosystem function do not occur. So trying to find out how much nitrogen or sulfur is too much and causes harm to the ecosystems. We try to promote understandings of critical loads and approaches to development and outreach, and while creating communication materials so they can be used in management and policy making. We have different working groups working on discrete efforts here and meet as a group, usually in person, twice a year at the NADP spring and fall meetings. If you want more information on NADP, please check them out on the website and sign up for any of the email listservs to stay up to date on the committees. And so with that, I will introduce our speakers today. First up is Jason Lynch. He's an ecologist with the U.S. EPA Office of Air and Radiation, the Atmospheric Program in the Clean Air Markets Division, and has been for the past 14 years. His work focuses on assessing the ecological benefits of EPA's air pollution emissions reduction programs, such as the Acid Rain Program and the Clean Air Interstate Rule, and the review of national ambient air quality standards. In addition, Jason has worked on the development and application of quantitative techniques and biogeochemical models for studying the impacts of air pollution on aquatic and terrestrial systems. Prior to joining the EPA, he was an assistant professor of ecology at North Central College in Illinois and has a BS in biology and geology from Brown University and a PhD in ecology from Duke University. We met Todd McDonnell last month, so he's going to be our second speaker, and is president and principal scientist at ENS Environmental, located in Corvallis, Oregon. He holds a PhD in forest ecology from Oregon State University, a master's in hydrology from SUNY College of Environmental Science and Forestry, and a bachelor's degree in applied environmental science from the George Washington University School of Engineering. Dr. McDonnell's research is focused on biological effects of air and water pollution, climate change, and environmental sustainability. Lastly, we have Leora Nanus, who is an assistant professor in the Department of Geography and Environmental Science at San Francisco State University. Prior to her current position, she worked as a hydrologist with the USGS for over 10 years with the Alpine Hydrology Research Group in Colorado. Her research interests include hydrologic and biogeochemical processing in undisturbed watersheds in the western U.S., including atmospheric nitrogen critical loads for aquatic systems in the Rocky Mountains. So I will stop presenting. Share your screen now.
All right. Okay, so Mike, can you see the screen?
Yep, you're good to go.
Awesome. The introduction. Today, I will be talking about aquatic critical loads, focusing on the acidification side. I will be talking about the history of acid rain and critical loads, how they're developed, and then diving into a case study looking at emission reductions since 1990 and exceedances. Following me will be Dr. McDonnell. He will focus on three case study areas and projects that he's worked on, working on in the Southern Appalachians, in a new study recently published in the Appalachian streams. And then lastly, some work he did with the U.S. Forest Service in Region 4. That will follow. Todd will be followed by Dr. Nanus, who will be talking about critical loads of nitrogen and aquatic systems in the Rocky Mountains. The story of acidification and critical loads really starts with Gene Likens and other researchers in their discovery in the 1970s that rain was acidifying. They determined the cause of this was air pollution. In specific, it was NOx and SOx from burning fossil fuels. This ultimately led to the formation of NADP and the monitoring of precipitation beginning in 1978. Early on as well, researchers were really concerned that the deposition, that the air pollution would ultimately deposit into our soils and deposit into our surface waters, causing forest acidification and also impacting our aquatic systems to acidification in these systems. This led researchers from EPA and others to really understand and try to understand the extent of the problem in the late 1970s and early 80s. They realized that acidification wasn't necessarily a national problem. It was located in areas that were sensitive. And to understand those areas, they went out and gathered up all the alkalinity, which is a measure of the acid-base balance of a stream or a lake, to determine whether an area is acid sensitive or not. And this is really truly a map that has stood the test of time, and it really shows that our acid sensitive areas aren't continuous across the U.S., but are dominated in the eastern U.S., the southeast, the upper Midwest, and the Great Lakes region, and throughout the West. This is important because this allowed this group of researchers to really focus their work. And they did so through large surveys that were probabilistic, looking at streams and lakes here. And here's a distribution of the lakes and streams that were sampled in the 1980s. And so you're probably wondering, why start and why talk about these important surveys that were done? Well, you're going to see that the critical loads that we have today for surface water acidification really are the backbone of these surveys that were done in the 1980s. These surveys followed other surveys, such as the EMAP program as part of EPA. It surveyed additional lakes and streams in the eastern U.S. were being surveyed, other researchers began to monitor lakes and streams in areas that were known to be acid sensitive. And here are three examples. This is Grout Pond and Big Moose Lake and Ronnout Creek. These are located in New England, Vermont. Big Moose Lake is located in our stream is located in the Catskills Mountains. They wanted to understand the level of sulfur in these systems. They wanted to understand the level of acidification that was occurring as well. And so what did they find? Well, in the 80s, they found high levels of sulfate, particularly very high levels in Moose Lake and Ronnout Creek in New York. They also noticed that there was low ANC values. ANC is a measure of the acid-base balance of the system, and in some cases, ANC has dropped below 0 in these creeks. All right, so what was actually happening to these? Sorry, So what was actually happening to these lakes and streams? Well, here's an early picture of the lake, Bear Lake in New York in the Adirondacks. And what you see here is this very crystal clear lake back in the 1980s. And so what was happening, these systems were acidifying, and as a consequence of the acidification, we were losing the aquatic system and becoming clear clear. And so yes, acid precipitation was in fact greatly impacting our aquatics, streams and lakes in our acid sensitive areas. This led to a series of monitoring programs. One of the longest programs is EPA, the EPA's long-term monitoring. Here's a map of the lakes that we monitor today. In fact, it's the longest running water quality monitoring program in the EPA as well. Other studies were being developed. The U.S. Forest Service had a series of watershed studies like Bear Brook, Inferno, Hubbard Brook, Coweta, Leading Ridge, and others. And the goals were to understand the long-term trends in acidification of these acid-sensitive areas, and understand the science. This led to the development of the National Atmospheric Precipitation Assessment Program. It was an important program. About $500 million was available to continue to understand acidification and ultimately provide recommendations to Congress on how to deal with this issue. And again, getting back to the idea of critical loads, what's the importance or the connection to critical loads? As you'll see, it's these critical monitoring programs and research, experimental research, that basically provided the data and the knowledge that we will use to develop the critical loads that we have today. Well, through all the assessments that EPA and others did, we all realized that acid rain was a major threat. The evidence was overwhelming, and Congress and the president at the time needed to act, and they acted. And in 1990, they passed the Clean Air Act amendments. As part of the Clean Air Act amendments, the acid rain program was formed. The acid rain program, the goal was to cap and trade, which is a novel program. They were going to cap SO2 emissions at 8.95 million tons. The program would be fully implemented by 2010. And so the goal was to bring these very high levels of sulfur emissions at least to below 8.95 million. NOx as well had a goal of 2 million tons. It's important to note that EPA went on, due to the success of the acid rain program, to implement other regulations that brought emissions down even further. There was a series of programs in the 2000s, like the NOx Budget Trading Program, CARE and CASPER, which were also trading programs as well. These programs were focused on attaining the NAAQS. Nevertheless, they all reduced and set a lower cap for sulfur and NOx. And so this is our current caps based on our programs that we have today. So how well did these programs work in terms of reducing emissions? Well, the story, as many of you know, is amazing. I think if you would ask Gene Likens, you would ask even Charlie Driscoll and a lot of other folks, or Tim Sullivan, who worked through these, that in 1990, if we could ever get below 1 million tons of SO2, they would shake their heads. That's crazy talk. And here we are. I know in terms of our programs, the last few years, a lot of the reductions have been driven economically through the switching from coal to natural gas. But today we're at below 1 million tons of SO2. We're also below 1 million tons of NOx as well. And as a result, we have improving environmental conditions. Here's wet sulfur deposition from NADP. Here it is in an average for 2017 to 2019. In terms of nitrogen, we've had good success in the eastern US. However, there are regions today that have increased with respect to the earlier time period as well. So it's a good, bad type of story as well. All right, so let's come back to critical loads. You know, what the emission reduction and deposition programs don't tell us is whether a stream like Decker Run in north central Pennsylvania is protected. In other words, is the deposition that we see today protecting this stream? And so this is a personal story for me. And Deckard Run in the 50s and 60s had fish in it. My dad used to catch fish in this stream. However, I've never seen a fish in the 80s, the 70s, and 80s and 90s that I was tromping through this stream. And as you can see here, the arrow indicates its location, that this is one of the most impacted regions of the Northeast due to acidification and sulfur deposition. And so the question is then, is this green, is this level of deposition protective of this system? And ultimately, this is a critical load question. All right. And then back in the 1980s, researchers also had the same question. They wanted to know, could they determine a level of deposition or a level of emissions that would be protective of aquatic resources? All right. This led to the development of the critical load concept in the 1980s. And aquatic critical loads, in particular, were some of the first ones to be developed here as well. And, in Europe, critical loads were really being spearheaded in the 1980s and 90s. And here's a subset of some of the papers that were produced early on. They embraced the concept and were working towards really developing it. For some of you may not realize that in the US, at this time, critical loads were also being developed. The group from EPA was taking the national surveys, the water quality monitoring data that we had at the time, and developing simple mass balance critical loads, because again, they were interested in this idea of how much deposition is needed to be reduced in order to protect our systems in this case. And so there is this rich history early on in the US of developing these critical loads. In fact, I actually have the data for the work that was done during this period as well. Well, unfortunately, in the mid-1990s, EPA published an acid deposition standard feasibility study, which was a report to Congress. And in this report, they were very critical of using or developing an acid deposition standard, largely underlines that there was too much uncertainty in order to do so. This put a halt to work at the EPA in further development of critical loads. Well, lucky for us, in Europe, it continued at a rapid pace. So this really was a delay or a hiatus in terms of the development. The good news is in the 2000s, critical loads reemerged. It was led by a different group. It was led by the National Park Service and the US Forest Service and individual researchers. And in 2005, a really important publication was put forth through Alan Porter, Tamara Blatt, Deborah Potter, and Sydney Huber, which really brought this concept back. Their goal was to bring it back and use it as a management, critical loads within a management context. At the same time, governors in New England were interested in critical loads, and so they had projects that they had funded to develop forest and surface water critical loads. Linda Pardo was a very important component of the work that went into developing some of those critical loads for the Conference of New England Governors and Eastern Premiers. In May of 2006, the multi-agency critical load work group met in Charlottesville, Virginia. It's brought together the National Park Service, the U.S. Forest Service, and USGS. And also this brought EPA back into the fold in terms of developing. One of the important components that came out of this conference was the establishment of CLAD in the fall of 2016. And so 15 years later, we've had many achievements and in terms of the US. And so that's just a little bit of history of where we came, and where and how critical loads were developed and where we are today. So I want to move on and talk about how we calculate aquatic acidification critical loads. It ultimately comes down to understanding the biogeochemical processes. And that's why the NAPAP work and the work that was done at the experimental watersheds are really fundamental to our understanding of these processes. We have air pollution. That air pollution can deposit to our forest. In doing so, it brings in the acidity into the system. That acidity increases aluminum. Aluminum is toxic. It can impact the trees. These are ions in solution. They can run off into the surface waters. They can be directly deposited in the surface water. Ultimately, that's increasing the sulfate, nitrate, H ions, and aluminum in that. And that's what our early monitoring system was showing. Ultimately, decreasing water quality, the pH in the A and C, and a combination of pH and aluminum can have adverse effects on our aquatic life in the clearing, making our lakes very clear. All right, so we can use this understanding the biogeochemical process to develop simple mass balance critical loads. And here's the equation. To understand this, you have to understand three main components. That's the base cation input component here, probably the most important component. Base cations come from weathering of rocks, and they also come in from deposition. And ultimately, in order to develop a critical load for surface waters, you need to understand the balance of base cations within the surface waters. And that can be done through the understanding of measuring the water quality and understanding what sulfate, nitrate, and base cation concentrations are. The second component is nitrogen. Nitrogen is acidifying component. It's also a eutrophying component as well, but it has a very complicated path. Sulfur is known as the mobile ion, where it enters the forest and then moves towards the surface waters. Nitrate is a lot more complex, or nitrogen is a lot more complex, because nitrogen can be taken up into the trees, and then these trees can be hauled off on furniture. It can be immobilized in the soil. It can also be denitrified. So the amount entering in the forest is, in many cases, a small fraction of what's in the surface water. And so you have to understand that process. Again, if you know something about nitrate in the stream, you can understand that process as well. And then lastly, you have to set an ecological protection level here. And the connection here with the simple mass balance is that if we understand surface water, we can then relate it back to the bio, because they're inherently linked. All right. In summary, we have simple mass balance that accounts for acid-base balance. That's the framework of the critical loads. We use water quality data in some form to estimate them. You need to know runoff as well. That converts the concentrations that we measure in the surface water to flux. And then ultimately, you need to calculate a base cation flux, or base cation weathering. Those are the most important. We have multiple techniques. We have a simple one like the F factor. We have more complicated ones like using dynamic models, or a combination of a dynamic model and a regional regression. And so let me just present a few examples here. Dynamic models are mass balance models. However, they are complicated models that factor in the bio, the soil, etc., in order to determine the water quality. We have two important models in the US. One is known as Peanut, and the second one is developed by Charlie Driscoll. We have Magic, which is developed by Jack Hosby. And these models have been fundamentally important to calculating weathering rates and also critical loads. Another example is a combination of the two, where we take our monitoring data, our long-term monitoring data from LTM, and our survey data, and we use our long-term monitoring data to calibrate them in Magic. We then can predict base cation weathering in a relationship across the landscape or through water quality through these relationships, and then predict what critical loads are across the landscape. Todd will be talking about this work later on. All right, so the last component is ecological protection, and here we can link water quality data that we take and relate it to the biological function that we want to protect. And so in this case, if we protect for an ANC of 0, you're protecting for, well, maybe a dead stream. If we want to have full protection, maybe that looks like we need to protect to 100, and then somewhere in between. There's three main ways I think of selecting an ANC. One is to protect for ecological integrity, which is a way to evidence approach. You can protect for a species, or you can protect for natural historical conditions. The way to evidence approach is really taking all of that information that I've learned from the work in NAPAP and moving it all the way to today, understanding how ANC and the responsive bio work. You can yard that up into areas where you then define, if I protect for an ANC of 20, this is what I'm protecting for. If I protect for an ANC of 50, this is what I'm protecting for, and so on. 20, 50, and 80, 20, 50, and 80 are the three most common critical loads. ANC limits that most folks use around. We can set critical loads for a species, such as brook trout, and this is work that Barry Baljico has been working on. Brook trout, he looked at density and biomass and determined the best to produce a minimum protection would be 25 or 50. And so on. Last, you can protect towards historical values like an ANC of 50 or ANC of 20 here as well. And we can determine these historical values through use of dynamic models. All right, so I've just talked briefly about the steady state models that are important to critical loads. There's also target loads. A target load is still a mass balance approach, but it has a time set horizon like ANC of 20 and so a target year of say like 2050, you want to achieve your ANC limit, or 2021 or so on. Typically dynamic models are used to do these. Here are two examples. Here's an example by Sullivan et al. That determined critical loads using a combination of Magic and regional regressions to develop target loads to meet an ANC of 50 for 2100. Another example here is in the Great Smoky Mountains National Park here as well, where Charlie Driscoll used the Peanut model at select sites and extrapolated it to the various streams within the park as well. And they had different goals of 2050, 2100, etc. as well. Okay, so just to summarize, our national surveys and our LTM programs are really fundamental in the basis for developing the critical loads that we have today. And here's our surveys. Not surprising, the critical loads that we use are a real function of them. We've expanded in terms of the water quality that we have. These critical loads, along with Todd McDonnell's work here in the Appalachians, are part of the National Critical Load Database. They can be accessed here through NADP. This database has other critical loads as pure, empirical, and herbaceous ones as well on that. Okay, so getting back to critical loads and just a short example, and in a short example, how has exceedances changed since 1990 in terms of our improvements here? And so I just focused on a case study area in the eastern US and New England. We focused on the Appalachian Mountains and the New England coastal areas. I looked at steady state models from critical loads from the database. I used an ANC of 50. In total, I looked at 7,781 lakes. It's important to note that my analysis really tells about these lakes and isn't necessarily representative of all lakes in the region. I looked at total deposition, all right, and so for the period before TDEP, I used wet to dry ratios to estimate those. And then I factored in error within that analysis. All right, and so this is what I have. And so in 1989, we had in red in terms of our exceedance. So these are lakes or streams that exceeded the deposition for that period. If it's in blue, it does not exceed. If it's in yellow, yellow are at the critical load within our margin of error. And it's important to note that not all water bodies that we have surveyed all over time are sensitive or were impacted here. And so these I just grouped as never exceeded the critical load. All right, and then lastly here, this number in the middle is the exceedance rate. And so let's just take a trip. And so I just made an animation here. All right, and so what we're seeing is as deposition decreases, more and more lakes that were exceeded, that aren't exceeded, and so our change in exceedances. First phase of the acid rain program ended in 2000 and so on. And then starting in the mid 2000s, we've had additional emission reduction programs coming in through EPA. In 2010, we have the full implementation of the acid rain program here. And through that, we have this steady decrease in the overall exceedance for this region. All right, and so by 2018, this selection of lakes, there was about 12% or 12% exceedance rates for the region. So super successful in terms of our emission reductions, improving our exceedances. All right, so let's just take a look at some water quality information, and let's link a long-term monitoring data of some of the lakes that we've talked about back to our critical load exceedance. And here's our Grout Pond in Vermont. This is the water quality trend, and you can see in the 80s, sulfates was well over 80, and now it's near about 25. And we have had a steady increase in terms of ANC. Quality are matching up. Here's Lake Colden in New York. Here in the Adirondacks, in the northern part, we see the same decrease in sulfur with a rise in ANC. And if we look at our critical loads. Here in 2014, we're shifting from an exceedance to at the critical load to a non-exceedance state. What's really neat about this lake is in the 80s, they sampled fish. In the 90s, they sampled for fish. And in both times, they were unable to find any fish in this lake. However, they did a survey in the 1990 and 2019, and they were finding brook trout again. And so there's been this kind of biological response as ANC and deposition improves. And so here's the case: our water quality, our critical loads, and our biologicals are all pointing towards recovery of these systems. Not everything is progressing everywhere. In some instances, this is Meadow Run in Virginia. You can see it still has a high level of sulfur in its watershed, and ANC really hasn't changed over the last 20 plus years. And if you look at the exceedance, we're still exceedance today. And in the South has a complicating of soils with a lot of clay that absorbs sulfate, etc. And so in many of these cases, this play between sulfur absorption has delayed recovery in these systems. The good news there is if a water body has a relatively higher ANC of 60 or more, they seem to be improving despite the sulfate absorption within that. All right, so I'll just end here, getting back to my childhood story. This stream does have fish in it again, and so deposition has improved to support it. In the case of Bear Lake, New York, here's a picture in 2016 showing probably what the lake should look like with the algae and photo in it. This really leads us to the question: will continued elevated nitrogen deposition cause eutrophication as we switch from lakes that were acidified to potentially lakes that were eutrophied? And so I think that's one of the concerns I'll leave you with, is that this, we've improved it greatly. Hopefully we won't go to the next level to eutrophy, but that's one area of research that we need to continue to focus on and do it. On that, I will end and quit sharing and have Todd begin sharing.
Yeah, and as Todd's loading up, if anyone has a question, feel free to raise your hand or take yourself off mute and ask it. Jason, one of the things you had mentioned in this was that you showed the response of brook trout to that level of ANC and the critical load, etc. How do different species respond to these changes in ANC? Is it all pretty much happening at that level, or how variable is it in these lakes and streams?
Yeah, so brook trout tend not to be a super sensitive species, and so they tend to be able to occupy surface waters even with ANCs that are probably below 20 in some instances. So there are some species that, given particularly if aluminum is low, can really come back into those systems, and so there's some acid. And so I would say the response would be very variable. Species like the black nose dose is a very sensitive species, and so for many of the streams they used to occupy, I think they'll take some time to reoccupy back as well in this case. And there's also barriers as well. The fish have to get back into the lake or stream as well.
Thanks. Any other questions for Jason?
Record metrics that would capture greening or browning in the lakes and streams?
We do, absolutely. The lakes in particular, they measure DOCs, so we know how they're browning. They measure sucky discs. They measure, some of them do chlorophyll A as well. And so, yeah, and so one of our, as part of that program, we're really focusing on looking at some of these other parameters and how they're changing and how that will impact acidification and how it will relate to eutrophication of those systems as well.
Thanks. All right, let's move forward. Todd, we can see your screen, so you can take it away.
Okay, can you hear me okay?
Yep.
Okay, great. All right, yeah. Thanks, Mike, for hosting, and thanks, Jason, for that great introduction and background and all that information. That was really fantastic. I'll be talking about those 3 projects that Jason mentioned, mostly focused on regional sensitivity, looking at critical and target loads, and to be used for natural resource management and for policy making. Slide's not going. Okay, use this. So yeah, so we have that Southern Appalachians work that we also refer to that as our EMDS project, Ecosystem Management Decision Support. And then the recently completed regional patterns in trends and target loads for Adirondack streams. And then surface water critical load assessment for U.S. Forest Service Region 4, which is the Intermountain region. It also includes portions of the Rocky Mountains. These are our collaborators on the MDS work in the Southern Appalachians. We had various topic area experts and ecosystem modelers and decision support modelers. This was a group effort. This is our study area. We have 7 national forests in U.S. Forest Service Region 8, and then we included the Monongahela National Forest as well from Region 9. These forests were monitoring quite a bit of water chemistry data. We aggregated that. That's these small gray dots, all the points in the forest where we have water chemistry data, at least one sample. Some of these are sampled many times. And the pink, we also aggregated data from other regional surveys as well. And then the pink triangle is a little bit tough to see on this one. Those are the sites where we were able to run the MAGIC model that Jason mentioned, the dynamic biogeochemical model, because we had soil chemistry there as well. So that allows us to run MAGIC. And that was important for this work. And I'll talk a little bit more about that in a sec. So like Jason mentioned, we used more of a kind of a trimmed down version of the SSWC model. We took out the nitrogen terms, so we're generating critical loads of sulfur in this project. We have that base cation balance where we have the inputs from deposition and weathering, and then we have the outputs, which is the base cation uptake and removal in any tree harvest, and then an ANC limit that Jason so nicely described. For our ANC limit, we specified an ANC concentration of 50 microequivalents per liter to be generally protective of the biology for this region. We could have gone higher, a little bit higher, a little lower, but we chose 50 to base most of our analyses on. So one of the trickiest terms to obtain for that equation is the weathering term. We ended up developing an approach that you got a little window into there from Jason, whereby we used the MAGIC model to generate what we feel are fairly accurate estimates of weathering at those 140 sites where we can run that more high resolution model. And then we took that and extrapolated it out to sites where we had the water chemistry and then sites to where we only had landscape characteristics. And that was more uncertain when we moved beyond the water chemistry, but we were still able to get estimates for the whole region. And so this is our resultant map, weathering map for the whole area. And so we can see that all the forests have at least some portion of the forest characterized with low weathering rates. And here's a side-by-side with the critical loads that come out of that equation. And you can see that the low critical loads, those sensitive areas, tend to be in the same areas where we have low weathering. So the weathering rate really is driving the train here. And if we have this regional picture of weathering, we can generate this regional picture of critical loads. So just to zoom in a little bit on the resolution of the data, we ended up generating critical loads for 140,000 or so stream segments throughout the area. And this is a picture of the black lines are 12-digit HUC. So it's oftentimes a management level HUC boundary. It's one of the finest resolutions put out by USGS at a national scale. We went finer than that, where we have critical load estimates for every stream segment within those 12-digit HUCs. And so this is a database that can be used very easily for fine scale management. So here's a zoom in even further to one of those 12-digit HUCs, and you can see the small little catchment polygons that we created. Those are based on the moderate resolution NHD. That's why they're a little bit coarser than this high resolution NHD stream network that's overlain on top. But in any case, we can take these critical load estimates at fairly fine scale, code them out to the streams, and you can really get a sense for where are you finding sensitive catchments and where you're not. And this also extends out to the terrestrial situation as well, but I'm not going to get into that for this talk. And there's a map of the critical load exceedance. It's also showing similar patterns to the weathering and the critical loads. Where you have low weathering, where you have low critical loads, you're going to tend to find your exceedances there, unless you're back to a background deposition scenario, because some of these critical loads are quite low. So we see exceedance throughout the area. I think there's at least some exceedance in every national forest. And when you have that spatial picture of critical load, a complete coverage, you can then look across the entire management unit and then characterize the portion of the forest or a wilderness area that is either in exceedance or out of exceedance. So these are the different exceedance categories that were on that previous map. And it's the area in kilometers squared and the percent of the forest that's in or out of exceedance and by how much. And so that orange and red boxes there, that indicates the percentage of the forest that's in exceedance. So in exceedance by some amount in the orange, and then by quite a bit in the red. And so you can see that there's not a lot of the area. This is based on 2014 deposition on average. So the picture would look a little bit different now because depositions continued to come down since then. But again, like I was trying to say, not a lot of area that's in extreme exceedance, but there's a fair amount that was in exceedance. And then you can break this down into whatever level you want to, in terms of wilderness area or particulars. There may be a particular timber sale that's going on, and you want to know about the sensitivity of the landscape in that particular area. And so the exceedance calculation, that just popped up a little too early, but anyways, the exceedance calculation is typically done for sulfur critical loads by the sulfur deposition minus the critical load. And if you have a positive value there, you're in exceedance. Well, let me see. Oh, I went away now. Anyways, so you can also include, like Jason was showing, you can address the nitrate as well, and you can either put those long-term steady state terms in the critical load equations, or you can address nitrate leaching while you're calculating the exceedance. And so if you include nitrate leaching, if you have an estimate of nitrate leaching for the stream reach that you're interested in, you can include that in this equation, and it effectively magnifies the exceedance of the critical loads for sulfur deposition. It's really you can consider it another stressor on the system. And in this area, we do have some regions that are leaching nitrate, and so these are the areas that it would be prudent to include that nitrogen leaching term into the critical load exceedance calculation. And that helps to give you a little bit better sense for what the exceedance is based off the ambient or the current day levels of nitrate leaching, because it's kind of it's a tricky thing to understand the future nitrate leaching. We don't know, we can't necessarily assume that all nitrate will leach going forward, but we do know what's leaching now if we do have a water chemistry measurement. So onto the Adirondack project that we recently completed in collaboration with several folks at Syracuse University and USGS. This work was wrapped up in a report for NYSERDA, the New York State Energy Research Development Authority. As an overview here, we focused on 25 intensively studied sites throughout the Adirondacks. And then we extrapolated those results from those intensively studied sites out to the broader region. And we had about 400 stream sites that we were able to extrapolate to. The main components on this project was we first ran a dynamic biogeochemical model, and that was developed by Shui Xiao and Charlie Driscoll at Syracuse. And then there was an episodic acidification analysis that was done by Doug Burns at USGS. The fish response functions were developed by Barry Baldigo. You saw a little bit of that from Jason's slides. And then we integrated those components and worked them together. I'll show a little bit more on that soon. And then regionalized the results for the trend in ANC and fish metrics, and also the results for the target loads for ANC endpoints. So those are our sites, and that's the pattern of deposition across the Adirondacks. And so PNET BGC was used for the dynamic modeling. That model allows for historical reconstructions of acid neutralizing capacity in the stream. So we can go back all the way to 1850, pre-industrial conditions, and get an estimate of what the stream condition, chemical condition likely was before elevated deposition. And then the model can also be used to look forward and evaluate future scenarios. And these are typically future scenarios of emissions changes that would result in changes in deposition. And we typically look at decreases in emissions and decreases in deposition. And then how does that play out in the stream system in terms of ANC response? In addition to these scenarios, these models can also develop target loads. And we developed target loads of NNS deposition with PNET BGC. And those endpoint years we used were 2050. The endpoint years we used were 2050 and 2150, and we used two different ANC criterion. We used a fixed ANC, so what would be the deposition to recover all streams or push all streams to an ANC of 20. Or we also used a site-specific ANC, which we defined as the pre-industrial ANC minus 20 microequivalents per liter. So the idea about the site-specific ANC was trying to protect the system back to at least close to where it was once prior to the Industrial Revolution. There was this episodic acidification analysis, like I mentioned, that Doug worked on, and streams generally show lower ANC at high flow. So either a storm event or a snowmelt event generally suppresses ANC and makes the stream more acidic. So Doug worked on this and developed these really a set of equations to estimate the ANC at any flow condition. And he used this great data set developed by Greg Lawrence at USGS using this regional stream survey. And this is where the 400 sites comes from. And so I'm not going to get the details of what Doug did, but basically this effort allowed us to adjust the ANC estimate based on the flow conditions at the sites. And then the third main component was these fish response functions that Barry worked on. And the fish response functions were based on summer base flow conditions. And so that's why that episodic acidification analysis really helped us, because the PNET modeling was done at high flow condition, and those ANC measurements were typically taken at high flow. So that episodic acidification function allowed us to flow adjust the ANC measurements to the summer base flow conditions, which are the conditions at which these fish response functions were developed. And these were response functions based on ANC to predict aspects of the fish community, including fish richness, brook trout density, and brook trout biomass, both as a probability and also absolute values. A lot of details there, but really we ended up integrating these three components where we took those PNET results and we used that episodic acidification analysis to adjust that flow so that we could use the ANC results in these predictive fish response equations. And that allowed us to estimate the trends in fish response metrics through time, not just ANC through time, but now we also are tracking the fish response metrics through time. And we did this for the 25 model sites, and we also did it for the 401 regional sites. So here's an example of the fish richness results for year 2050 under the business as usual emissions scenario. Business as usual means ambient deposition, ambient emissions moving forward out to 2150 and even beyond. So this map shows the probability of having at least one fish in the stream. So the red dots are the streams that have a low probability, the probability below 75% of having at least one fish. And the blue dots are those streams that we expect to have at least one fish, more than 75% chance of having at least one fish. This is under business as usual emissions. Then when we switch to an aggressive emissions reduction scenario, so decreasing emissions from where we are today, we expect additional recovery, biological recovery, all else being equal, with emissions reductions moving forward. So we have fewer red dots, more blue dots, more streams where we expect to have at least one fish. We also extrapolated the PNET BGC target loads to the regional set of streams. And here's an example for year 2050 based off that site-specific ANC endpoint. That's that pre-industrial ANC minus 20 microequivalents per liter. So we're really trying to get back to what was once there. And here's an example of an equation, regression equation that was developed to predict the target loads, the site-specific ANC target loads. So it's based on the ambient ANC concentration, so the ANC that we have today, and then we include in the latitude of the site, the elevation, and then the extent of the deciduous forest within the watershed. So we use those parameters, and we can predict the target loads at all these other sites. We see widespread low target loads for this site-specific endpoint. Next slide showing widespread exceedance of those target loads. And so, when you're looking 30 years out, that's just really not a long time, given the extent of soil-based cation depletion that's occurred in this area, and coupled with the low base cation weathering rates to replenish that soil-based supply. So when you look at these target loads and you have this time period, that's very important because it gives you a management time frame to work from, and it gives you a better understanding of how long things are going to take. If you looked out to 2150, we'd see fewer red dots because we're given more time to recover. This is the set of publications that came out of that work for future reference. There's a lot of details here, and it's all just finally documented. Everything is wrapped up. So real quickly here, Leora needs some time. I'm going to move through quick on the Region 4 assessment that we did for critical loads, Intermountain West, in collaboration with Jill McMurray and Meb and others at the Forest Service helped as well, and other folks as well. Contributing critical loads was huge on this project, and there are 12 national forests in Region 4, 49 wilderness areas. We characterized all those areas. We included lichen critical loads from Linda Geiser. We included the tree growth critical loads that were developed through EPA and the Kevin Horn's analysis, tree growth and survival. But for this talk, I want to highlight the fact that we brought in the surface water acidification critical loads and the surface water eutrophication critical loads that Leora will talk about soon. We reported on the location of the critical loads and their exceedances, the magnitude of exceedance, and described the resources that would be expected to be that Jason had on the screen for the U.S. earlier. Had a few points here in the Uinta-Wasatch Catch National Forest, and this is showing the exceedance of the critical load. So some areas not in exceedance, others are in exceedance. It's fairly high deposition in this area. This is a map of the exceedance of the eutrophication critical loads. Those critical loads tended to be lower, so there was generally more exceedance of the eutrophication critical loads. And we mapped this, we wrote it all up in a report, We summarized it into data tables, made it available to the Forest Service, and then Jill is taking the lead on a general technical report to be in park management and for other purposes. So I'll stop there, and if there's any questions, I'd be glad to take those.
Thanks, Todd. That's great work. Does anyone have a question for Todd as Leora gets her presentation set up? So, Todd, like, what kind of data, like if it was someone from a national park or a national forest, would they need to develop these types of analysis for their area of interest?
Well, I mean, a lot of the data are available. I mean, to start from scratch to generate critical loads takes quite a bit of information and the base level information. But now that, a lot of the reason why we're doing this is to put information in a usable format that folks can use in these individual management units. So that, for example, that EMDS database, the forest in Region 8 have that database and they can use that for their purposes. Same thing for the Region 4 analysis. Those data have been delivered and they're usable. The National Critical Loads database that Jason's been administering, that's a great resource of information. The CLAD mapper, the critical loads are out there. There's many of them, and sometimes maybe there's too much information, but it's there. It can be used, and there's folks that can help interpret the results.
Okay, great, thanks. Any other questions for Todd? All right, well, just to make sure Leora has her time, let's, Leora, we can see your screen and you can take it away. Cannot currently hear you. All right, now we can't see your screen.
Okay, got
Okay,
it.
now we can hear you though.
Okay, so can you hear me and see the screen?
Yes, you're good.
Okay, I've been teaching on Zoom all semester and we don't use Teams, so bear with me here, but I think we've got it going. Okay, so you see the full view. So thank you for the introductions and for the opportunity to share this work with you. And thanks to Jason and Todd for setting the stage on this important topic. So I'll be talking about critical loads of atmospheric nitrogen deposition for aquatic ecosystems in the Rocky Mountains. So I'll be focusing on alpine and subalpine areas. And past research has shown that pollutants, including nitrogen deposition, have altered these sensitive resources, including soil and lake chemistry, which I'll be focusing on today, lichen, alpine plants, and aquatic plants. So linkages between nitrogen loading and nitrogen export in surface waters is complex due to interactions between hydrologic and biogeochemical processes and pathways and watersheds. So for example, residence time of water in a catchment can influence water quality because many biogeochemical reactions are time dependent. And atmospheric nitrogen can be deposited directly to terrestrial or aquatic ecosystems in a watershed. And it's the transformations that occur in soils, plants, and microbial activity that greatly influence the form and concentration of nitrogen that can eventually reach surface waters and affect aquatic ecosystems. And there's knowledge gaps that exist in linking water and nitrogen cycles across scales that are relevant to ecosystem function, human interaction, and management decisions. So I agree with Jason's point effects of excess N deposition to watersheds, which can lead to acidification of lakes, nutrient enrichment, and changes in aquatic ecosystems. Eutrophication, as you know, increases primary productivity in lakes and can alter diatom species distributions that form the base of the food web in many high elevation lakes. So past work has connected increasing rates of nitrogen deposition with observed effects across the Rocky Mountains, including elevated surface water nitrate concentrations, episodic acidification of surface waters, and changes in diatom species shifts indicative of nitrogen enrichment. In the Western US, ecological effects are found adjacent to urban and agricultural areas and can include high nitrogen waters and altered plant communities, such as unnatural rates of forest growth and loss of biodiversity. Areas where this has occurred is shown on the map to the right here. And air pollution damage in these areas can alter ecosystem services that humans depend on. And these synergistic changes to soil, water, and biota can influence the adaptive capacity to respond to future disturbances such as climate change. So alpine and subalpine watersheds are particularly sensitive to atmospheric pollutions because of their high elevations. Deep snowpacks, where pollutants are stored for 6 to 8 months seasonally, and 80% of pollutants may be released in the first 20% of snowmelt, impacting local streams and lakes. Also due to short growing seasons, poorly developed soils, and exposed bedrock. So why measure the water quality of lakes in these environments? Water bodies react to deposition faster than terrestrial ecosystems do and may be susceptible to acidification and eutrophication. They form the headwaters of major river systems, so changes in water quality of the headwater system affects not only fish, wildlife, and ecosystem. So this is a simplified model of the nitrogen cycle showing biological processes that affect nitrogen flux. Forested ecosystems are generally nitrogen limited, meaning that they have efficient internal nitrogen cycling, and there's minimal loss of inorganic nitrogen to surface waters and groundwater. When the availability of inorganic nitrogen exceeds the total combined plant and microbial demand, nitrogen saturation can occur, and researchers have shown that this is occurring in high elevation watersheds in the Front Range of Colorado, Williams, Bering, Campbell, and others, just to name a few. And this can lead to increased rates of inorganic nitrogen leaching to aquatic ecosystems, increased leaching of acid minerals from soils to surface waters, elevated rates of nitrification, acidification, and eutrophication, and over time, a potential decline in fish populations and plant communities. So our question was really, how do critical loads for nutrient enrichment effects of nitrogen deposition relate to basin characteristics that vary spatially across the landscape? And so I'll draw on multiple journal articles shown here that were published in the Rocky Mountains, mapping critical loads of nitrogen deposition, and particularly focusing on more recent work in the greater Yellowstone area. So I like this figure. I'll start with this continuum of impacts to ecological health. This was developed for Rocky Mountain National Park, keeping in mind that every region's continuum or conceptual model may be different. But it shows current effects that include changes in soil and water chemistry, changes in aquatic plant species composition, surface water nitrogen saturation, and changes in alpine plant species and chemistry with current nitrogen loading, and then potential future effects over time. So resource managers have regulations such as the Clean Air Act and others to maintain these areas in pristine conditions. These lakes are often be logistically difficult to monitor long-term change in these environments due to funding and access issues. So in these environments, regional water quality risk assessments are poorly understood because of limited data for calibrating the models, and deposition is difficult to quantify in this topographically complex terrain. So I'm going to be focusing next on specifically the Greater Yellowstone area. This map shows deposition monitoring sites within the GYA. The snowpack synopticals are the NADP sites. The approach for this work to map critical loads of nitrogen and exceedances was to first develop create average annual deposition estimates of inorganic nitrogen, wet only, and also total nitrogen, wet plus dry, for the GYA, to develop predicted surface water nitrate concentrations using basin and to identify a threshold nitrate value using diatoms as an indicator of ecosystem health. And then finally, map critical loads of nitrogen and exceedances across the GYA. These are some plots from the Wyoming 8 site in Yellowstone National Park showing nitrogen and ammonium in precipitation with significant positive increasing trends over time. The map on the upper right, this was pre-PRISM, shows the NADP site high elevations due to the fact that they're logistically difficult to maintain. So the USGS Rocky Mountain Snowpack Synoptic was initiated by the USGS, the National Park Service, and the Forest Service in the mid-90s to complement NADP at high elevations. These samples are collected once annually, and they're useful for comparing deposition across the Rockies. And snowpack chemistry data is available from 95 to present day. And this plot shows increasing ammonium in snowpack at Lewis Lake Divide in the GYA. So it's consistent with what we see at the Yellowstone NADP site. I just want to point out that the composition of nitrogen deposition in the GYA, due to increased agriculture in the Snake River Plain, there's a larger contribution of ammonium and ammonia contributing to nitrogen relative to nitrate in more recent years. On the right, we have 2016 to 2018 compared to the left, which is 2000 to 2002. So the first step in this approach was to create average annual nitrogen deposition maps. The one on the left is represents Crete snowpack chemistry data for inorganic N, so nitrate plus ammonium, combined with the NADP wet chemical concentration data and multiplied with PRISM. And then the map on the right uses the TDEP model dry deposition, and that's added to the inorganic nitrogen wet deposition to get average annual total nitrogen deposition across the region. And that's why you see its coarser resolution on the right. So the next step was to develop spherical models for surface water nitrate using basin characteristics and the modeled N deposition. For the Greater Yellowstone area, we had surface water nitrate at 125 lakes based on synoptic sampling and other researchers over the years. The most significant basin characteristics in relating nitrate to these explanatory variables were percent barren land, because the vegetation is not taking up the nitrogen, total nitrogen deposition loading, and the percent steep slopes, which is a representative of flashy hydrology, and also thin and poorly developed soils. So this map represents predicted surface water nitrate across the greater Yellowstone areas, with predicted nitrate being greater than 8 microequivalents per liter in some areas. This is based on the regression model. The next step was to identify a threshold nitrate for surface water by relating nitrate to lake diatom community structure and identifying the concentration at which diatom species shifts occur. And this slide is some work by Saros and others showing the timing of changes in 2 key diatom species, showing that it's earlier in the Colorado Rockies compared to the Beartooths. But nevertheless, there is a response in the diatom Astronella formosa in the Beartooth wilderness lakes. And that's what we used for our threshold value. So the results of the growth kinetic experiments show that maximum growth is first achieved at 5 micrograms per liter. And this sets a surface water concentration that elicits a major change in this species, and it may actually be an overestimate. So a more conservative approach would be to take half of that, since that still increases growth and you start to see a response. So we tested multiple nitrate thresholds. I think that's a nice theme in the talks that were given today, is really looking at multiple thresholds. So 2 were based on the literature. That's the lowest one from Saros, as well as 1.6 from Theobald. I'm going to show results using 1 microequivalent per liter as the nitrate threshold in between the 2. So we rearranged the regression equation to solve for total nitrogen deposition, critical loads. And this is what it looks like across the GYA. The low critical loads, less than 1.5, are found at high elevation and show spatial variability that's consistent with differences in basin characteristics. Using that same threshold, we looked at exceedances of critical loads, and we found that approximately 30% of the GYA is in exceedance using total nitrogen deposition. And so keeping in mind that that's wet plus dry, we compared this with previous work across the Rockies, where we found only about 12% of the GYA was in exceedance using just wet alone. So I think it's really important to include dry deposition in these estimates. Some limitations to this approach: the critical loads and exceedance estimates are very sensitive to basin characteristics and the nitrate threshold value that's used. There's uncertainty in that value and uncertainty in nitrogen deposition value as well. We did find hotspots at high elevations for both inorganic nitrogen and total nitrogen deposition. Sensitive surface waters at high elevations are a function of barren land, steep slopes, and total nitrogen deposition. We found high spatial variation due to differences in basin characteristics. And these results can be used to help identify and protect sensitive ecosystems that may be impacted by excess nitrogen deposition in the GYA. The next steps were to conduct lake sampling within the GYA to validate the critical loads models and maps, and to look at changes in exceedances over time. And so we went out and sampled 9 lakes across the GYA in 2018. We collected complete sediment cores and water samples from these lakes. We're still working up this data, but preliminary results show good agreement between predicted total nitrogen deposition and exceedance versus the measured lake total nitrogen. So we're in the process of comparing pre and post 2012 end deposition based on the results of the lake sediment core data. That should be coming out later this year. So in conclusion, aquatic ecosystems at high elevations in the Rockies are sensitive to total nitrogen deposition. Critical loads and exceedance maps show broad areas of the GYA that may be impacted by excess total nitrogen deposition. And these approaches can be adapted to other sensitive indicators or ecoregions in the US and beyond. And then just quickly mentioning a couple current projects. One, given how important the nitrogen deposition estimate is to these critical loads, we're comparing measured and modeled nitrogen deposition to help inform these critical load and exceedance estimates in Western US national parks. And that's in collaboration with Mike Bell and others at the Park Service. And also looking at sources of atmospheric nitrogen deposition across the GYA using nitrogen isotopes in multiple ecosystem indicators, including lichen, snowpack, bulk deposition, and alpine lakes. And this is in collaboration with Jill McMurray and others at the US Forest Service. And I just want to acknowledge my collaborators and many thanks to others that were involved in this study and external funding sources. And questions?
Thanks, Leora. Is any questions for Leora?
I know we're close to time on this. I tried to get through it.
No, that was great. I guess like in relation to some of the other talks, like with the biological responses, I know obviously you're talking mostly with nitrogen here. Like, are there similar sulfur levels for species in the West, or how different is this? Or do you know the species level responses with this, with your numbers?
Was that for sulfur, did you say, or did I mishear you?
Yeah, initially I was asking about sulfur, just kind of in relation to what was going on, just like as an addition to what you presented, but also are there more nitrogen-based responses to larger biotic organisms?
Yeah, so two parts to that. One is we've looked at incorporating sulfur also. Haven't done it yet, but that's a good idea. We've done some preliminary analysis with that, actually in Yosemite. And the second part, with the diatom work, the idea is that because it's at the base of the food chain, starting with the most sensitive, will thus be largely protective across other aquatic ecosystems. But yeah, we haven't looked specifically at different fish species, for example. But that's a good question. That would be a good next step. Yeah.
Any other questions? All right, well, thank you to our three speakers, Jason, Todd, and Leora. Really appreciate you taking the time. Thank you to you all for attending this seminar. The next talk is going to be June 23rd on soils, mycorrhizae, and soil microbes. I hope you all can join us. I'm really excited about this one because I think I know the least about it of all the ones we've done so far. So thank you so much, and we'll see you next month.